So, good afternoon and welcome to week 2 of the live interactive session of a brief introduction of microsensors. The course instructor is Professor Santanu Talukdar from ICER Bhopal, and I am the PMR of teaching assistant Vikas Pandey from IIT Jodhpur. This is a brief about me and the class link, the YouTube channel, and my contact details in case you need to contact me. So, before starting the topics we have that has been covered by Sir in this week, any questions related to any topic you can ask? Yes, anyone? You can unmute and speak up.
Sir, just now I have completed only two lessons, sir.
Okay,
I came across only the definition of the pull-up voltage, sir.
okay, okay. So let's summarize the things that has been taught. I will not go like in details of derivation and all that. Anyway, you can see there. I'll be directly talking about formulas and what are the practical aspects of this. You can have discussion over it, and then we will have we will be solving some questions related to the topics covered in this week. Okay, so first is electrostatics. So in this actually we talked about some fundamental things, generally what we have already covered in our intermediate classes, you can say. Yeah, before starting, I think you two are new, right? Ven uh, Venkata and Vidisha, what is your academic background, like in which year you are or what branch you are? Hello.
Sir, first year electronics and communication.
Okay, and Venkata. Okay, Surya people left. Okay, so I assume most of you are above class 12th or intermediate, you can say. So I I think you have covered these things like Coulomb law and these things. Anyway, sir have also discussed that in the first lecture, electrostatics. So when we talk about electrostatics, we deal with electric charges at rest. That means they are static charges and their interaction. So the purpose of discussing this is that when we are talking about uh, micro uh, micro devices, that means micro electromechanical systems, there in the previous week we discussed that uh, electrostatic and gravitational force are not relevant. Gravity are not that relevant. But still we are talking about this because we can purposefully uh, use these uh, forces like electrostatics to create some wonderful devices that we will be seeing in the throughout the week, as well as how it is fabricated in the next week. Okay, so just to revise, the Coulomb law defines the force between two charges separated by some distance r. So it is given by, the force is given by 1 upon 4 pi epsilon naught q1 q2, where q1 and q2 are charges, and r square divided by r square, that is r is the distance between these. So the corresponding electric field is force divided by charge. And we have also seen that the capacitance of a parallel plate capacitor, that means uh, simply speaking, two conducting surfaces separated by a non-conducting material, dielectric or air. In this case, the capacitance developed will be epsilon A upon T, where epsilon is the dielectric constant of this dielectric or air, whatever is the medium there. Fine. So if we have two plates, that means when we are showing this image as very big, it is showing a distance like a large distance d. But in actuality, when we are talking about capacitors or even MEMS capacitor, the distance is very, very less. Even the real capacitors that we use in our everyday life, the distance d is very less. It is actually like one thin sheet of aluminum or copper, then another sheet of dielectric like paper, and another sheet of metal like aluminum. So the gap is actually just one or two paper thick, not more than that. So the D is actually quite less and A is quite high. That is the surface area of interaction. That is why we get large capacitance because we need larger area A and smaller distance D for a larger capacitance. Okay, so it will there are two factors that will define it. The capacitance, that is the distance d, and here we already know that our dimensions are in micrometers, so the distance will be very, very less. So that is one advantage, that using MEMS system we can have very high capacitances in small area because d is very, very less. And second thing is that we can control the charges based on the voltage we apply, positive and negative or 0 volt. Okay, so how these structures are actually made in MEMS structure. So MEMS devices use electrostatics for actuating and sensing. Actuating means where we need some work to be done, like motor is an actuator. So some work to be done, like pushing something, pulling something. These actions are called as actuation. Second purpose is sensing. Sensing means, sorry, suppose that we want to sense the pressure. So due to like suppose there is a MEMS capacitor structure, and then due to like we have fixed one part that is on the substrate. Maybe this is opposite, that below we have a fixed electrode and above we have a moving electrode. Moving electrode in the sense it is over a membrane, a very thin membrane structure. So let me draw it somewhat like we have, say this is our silicon. Okay, mostly MEMS structure we are making in silicon as we discussed previously. So let's say that inside it, what we did was we created a cavity kind of structure here. So this is the top surface, this is the bottom surface, and we will see about how we create such a hollow structure in silicon. So we etched out or removed this lower part, okay, lower part, and so we achieved something like this. Now we can have one electrode here. This becomes one plate, metal plate, and we are giving say plus 5 volt or plus 0.3 volt or something like that. Then on the top also we create some structure, say we create a we create a cavity such that we have a hanging structure here. Cantilever, we talked about cantilever in the previous class, and then we have such hollow structure here. Now we are connecting this to say 0 volt or ground or negative potential. Fine. So, am I audible? Hello. Can anyone confirm? Am I audible?
Audible, sir.
Okay. So, can we say that this distance, the whole distance here, can be ideally if we take say 3-inch wafer, 3-inch like this small 3-inch wafer, it will be 350 micrometer. This thick only is the whole wafer thickness, very thin. Okay. So now you see this whole structure can be say 100 or 200 microns, 100 micrometer. Okay. So we have edged out. So the total distance D here can be around 20, 30 micrometers, or say maximum say 50 to 100 micrometer. Okay. So let's assume 20 micrometer. So now can we say that it is a capacitor structure? Yes. Can it be called as a capacitor?
Sir, capacitance is defined between two metal plates. Now here,
Hmm.
one is given 5 volts, and that is on bottom side.
Hmm.
But I am not able to understand the top figure
Top also
where
here
it
we
is
are,
looking like isolated one. It is looking like
yeah, both we are putting metals, or even if it is silicon. So silicon is a semiconductor. So in if we dope it properly, it can work as metal. Like it can work as a conductor. So in that case, will it be a capacitor? Sili Silicon have the property to work as a insulator when not doped. But if we do doping properly, like I am not discussing the full details here, but let's assume that we have doped this top area and bottom area properly to act as conductors, or act as yeah, conductors, let's say, very highly doped n type areas. Okay, will it then work as two parallel plates? Yes, anyone? Please feel free to speak up. It's not a exam, nothing. We are just discussing, understanding things. Okay. Yes, let
we
me
should
ask.
create an insulating layer, sir, with SiO2, I think.
Yeah, in between there are two options. We can have SiO2 layers, or here why I am purposefully saying it as hollow structure, that is air. And air is also a dielectric, because in this structure what we are doing is that suppose that we want to sense the pressure being applied on the top. Okay, so due to the pressure that gets applied here, say this green one is the pressure, some pressure gets applied here. So what will happen is that this structure will bend, this red structure will go down, and as such, like it will bend a bit, and as such we will get the distance d will decrease. In this case, the distance between the two electrodes will decrease, and thus we will have a uh, different capacitance. There will be change in capacitance, and this change in capacitance can be used to sense the pressure. So such structures are there. In some cases, it is even made that it is just a membrane kind of structure, and on the membrane we are putting some resistive materials, like we are depositing polysilicon and then doping it properly. And when some pressure is there, this whole membrane will bend. So due to this bending, the structure will get elongated, and due to that elongation there will be change in resistance. So that also is a way of sensing. So that is when we are using this what you say, resistance or piezoelectricity as the sensing mechanism. When we are talking about capacitance, there are such mechanisms where the distance is changed or the area between area of the expose area of interaction, the surface area A is changed. So the electrostatic force between these two plates will be given by epsilon A V square upon 2D square. So V we are keeping fixed, A we are keeping fixed since there is no change in cross section, but we are changing D, that is the distance between plates. And when such structures are made, they can be used for sensing as well as in some cases we will see in the next slide as motors. So any doubt till here, anything you are
Sir,
not? Yes.
why two is there in the denominator, sir?
Hmm.
Two
That if you see sir's
derivation, sir.
derivation,
Okay.
yeah, sir is deriving everything. I'm just putting here the formulas directly so that we can discuss further, right?
Okay, sir.
Yeah. So that's equations sir have derived already. So you can check those videos. Okay. So this is the fundamental of MEMS capacitive structures. And capacitive structure like parallel plate MEMS capacitor can be can be used for actuation as well as sensing. So we can make some movement due to this as well as we can do some sensing means detecting something. It can be pressure, it can be gas, it can be some temperature, humidity. It may be that due to temperature, rise in temperature, this structure is moving away, coming close, something like that. In that case also, we will see some change in the capacitance. So how does this actuation works? That means how the movement of this parallel plates due to electrostatic, force occurs. So electrostatic force is used to move MEMS component, that is to have some actuation. And force between two plates is given by PC upon X. That means change in when we are wherever we are putting differentiation, that means change in the capacity, change in that factor. So change in the factor C, that is change in capacitance, and V square is fixed, that is the voltage being applied. So half dc dx, that means change in capacitance. So when we are putting two electrodes, one fixed electrode and one moving electrode, okay, then there is some field and the field will change. So how we can change this? One is when there will be some movement, the capacitance will change. The other is if we are changing some voltage, we are giving some control mechanism to change the voltage. So due to the change in voltage, it will try to maintain that field, and as such, the movement of this will occur. And how this movement occurs, that we can see. Okay. Yeah, first is the voltage and displacement will have some relation. Okay, so let's suppose that we want to pull this moving electrode, we want to pull towards us, so we will apply some voltage. When we want to push it away or we want to have it at equilibrium, a voltage has to be applied. So the control is in terms of voltage. So if we plot it in terms of the electric potential that is given on the fixed electrode, moving electrode is 0 volt, that is fixed. Fixed electrode means the position of electrode is fixed, but voltage is variable, is varied. So the control signal will be in terms of voltage, pulses, or maybe where the voltage levels will be different. So if we see a plot of this, how the position will change. So you see higher the, like we are defining one mean position, x and y position. Okay. So this is the mean position, that is from where we are saying that it is moving closer or away. Okay. So to move it closer, we are, you see, we are putting some voltages, lower voltages. Then to move it away, like in negative direction, how the higher voltage is to be applied to move it away. This is just a simulated representation, not an actual one. We'll see some actual images also. So how this pull-up effect in MEMS is done. So as the voltage increases, the plates get closer. That means it will, the distance x or y, whatever we take, that becomes negative. So suppose that this is the fixed plate and thing, and this is moving plate, and we are putting a scale and we are putting 0 here. So when we want to make it closer, that is in negative directions, what we do is that we increase the voltage, and when we want to make it further, like farther away, we put some lower voltage or negative voltage. So what will be the pull-in voltage? That is when the voltage will overcome the mechanical restoring force, because these are physical structure, they are not in air. When we are talking about plates, we are not talking about we are keeping some plates in vacuum or something. These are physical structure. They can be on, you see, like they can, if we see the top view of a wafer, this is a wafer, say we have cut out a hollow part, and these are two areas, and in which we have coated these two sides as conductors. We have put, say, gold, aluminum, or we have doped this area to act as electrodes. Now this will come closer, but it is limited by the mechanical force because it already have some strength. It is a physical object, it is fixed. So the movement will only occur when the electrostatic force, that is the force due to the field that we are giving, the voltage we are giving, is like is able to overcome the mechanical force that is there, that is trying to pull it to its mean position, say 0. 0 position we are saying, that is the original position. So it will try to remain there. That is due to the virtue of it, since it is a physical object, and it will try to remain there. So this force is given by this voltage V pull in or Vp is given by under root 8k d naught q upon 27 epsilon a. Again, the derivation you can see in the sir lecture. Okay, so displacement versus voltage. If we plot a curve, we'll see that there is no displacement for, like, the displacement is negligible till some voltage, and at one point this displacement will rise, and this point is known as V pull in. That is, it will try to pull the whole structure closer and will try to like remove the gap. Okay, so this is the maximum voltage that we can go for uh, before breaking, like before breaking the structure. Okay, so how these systems are coupled, or how these systems are made. Okay, so the equation, the total is something like to be in equilibrium, the mechanical force as well as electrical force should be equal. Whichever is higher, we'll try to overcome it. So if we see a structure where we have anchored it, and let's say that the spring constant, like whatever the structure we have made, it has some spring constant, since it is a like silicon. If we take PET or whatever structure we take, say sometimes even these structures are made using silicon nitride and this thing, they have some mechanical properties. They will have a tensile strength, everything. So due to this, we can in mechanical sense, we can assume it having a spring constant, it to have some force that is pulling it up, and we can represent it easily using the spring and mass system, and we can have find the spring constant K. So due to this spring constant K, it will try to retain its position, and as such there is a mechanical force Fm. Okay, and which we can give as this m x double derivative c single x single derivative kx. Okay, these are m, c, and k. These are constant. Okay, so we can say that to have the equilibrium position, our electric field. Now we again know what is the electric field. That is given by, here you see, half dc 1x v square. So 1 v square is, v is one component, capacitance, change in capacitance is another component. So we know these components, and based on these components we can have like different position, different value of f, not f, sorry, different value of voltages that will determine what will be the position. This force, this electrostatic force, will determine the position. So this is when we are talking about in case of actuation, where we want the part, the cantilever or any other structural part of the MEMS device to move, to have some action. Okay, so then again there are some other factors like due to this mechanical force not being uniform, it will change over time, so there will be damping. So due to this damping, these resonators or these actuators will suffer some loss over time. Over a period of time, this this movement will get disturbed. It will not remain the same. As well as uh, we want that this movement should be replicated again and again. So to have this perfect replication, we want that there is no damping. Damping factor is almost 1, so that over time we will have similar kind of, what you say, similar kind of interaction. It should not be that in first run it moves with say if you put 5 volt, it change 10 micrometer distance, and second time if you put 5 volt, it changed 20 micrometer, or say let's say 5 micrometer only. Then 5 volt next time it just moves 2 micrometer. It's not of our, like, it will not be beneficial for us. So we want the structure to be such that the damping factor is 1. That means every time we put same volt, same movement occurs. So in seeing all this, you can see that why material selection is important. In the previous class, one question was there that what is the most common material that we choose for MEMS devices. So I said there are two regions. One is that it has very good mechanical strength. It has due to its properties, like it is having good stable mechanical properties established over a period of time. One reason. Second is obviously that it is very well known, and it is readily available in semiconductor industry, and that's why it is very easy to adopt that. That is one commercial reason. But another reason is that there is no other material so easily available and so uh, what you say so readily explored that can be used to uh, replace this silicon. That is the reason that we generally work with silicon in MEMS actuators and sensors. Okay, so what is the stability? I said that electric force and mechanical force should be in equilibrium. That means the stability will be achieved when the restoring force is less than zero. That means the difference in force is uh, what you say is nullified, and due to this there is no change in the restoring force. That means either electric field is not changing as well as neither electric field nor mechanical field is changing. So if we plot it, let's say it is again a simulated graph, that displacement and force will be like will be represented by such a graph that if this is the pulling point of the field electric, so there will be a mechanical restoring force that will try to increase with its distance. As we increase the distance due to this voltage, more mechanical force will be there, mechanical restoring force, and it will be nullified due to the larger electric force. And as such, we will get a equilibrium position, that is, it is fixed at that position. And what happens if we are changing this electric field? Yes, anyone who thinks what will happen if we are changing this electric field in a sequence, what we will see? Yes, anyone, any guesses?
Sir, repeat the question once more, sir.
Yeah, the thing is that we are saying that we have mechanical force uh, trying to retain the position of our one moving plate. Other is that we are putting some voltage to change the position, right? So once we attain equilibrium, the movement of this, say, this is our fixed plate where we are putting some voltage, and this is a moving plate. Okay, so due to this, uh, it is fixed to a structure. We are saying that due to this spring constant K. Okay, now due to some voltage, say V1, I am able to change its position and get it here. Fine. What will happen if I am not fixing this voltage, but instead of that, I am giving a voltage like I am giving 0 volt, then V1, then again 0 volt, then V1, like this. So what will happen in this case? Yes, what will happen when we are giving changing voltage? Let's assume only two level of voltage, 0 and V, or say 5 or 2 volt, whatever is the value of V1. So what will happen in this case? Any guesses? Yes, anyone can speak. There is no restriction. Yes, please. Or should I ask someone? Yeah, Vidisha, are you there? Vidisha Mandal. Yeah, please don't be shy, not an issue. You might be wrong, but you should try,
So
please.
the pull-in point may be changing, sir.
Okay.
Pull-in point. Pull-in point.
See,
Earlier,
hmm, we are putting a voltage to pull it. It comes near. What happens if we remove the voltage? What will happen? Yes, anyone? This spring constant or the mechanical force is still there. It will try to pull it back to its position, its previous position. Am I right? Yes, anyone? Now we
then the bottom plate will stuck to the that position, sir.
bottom plate is already fixed. Upper plate is moving.
Okay, sir.
Okay. So when we are changing the voltage, like first is we are able to pull it, okay, or we are able to push the plate. But what if we want this to happen in a specific sequence? Suppose that we want to create uh, this moment we want in a frequency. So such things can be controlled using the voltage that we are giving. We can even give some sine waves where this moment will be very smooth with the frequency of the sine wave. Suppose that the frequency is 20 hertz. So the moment of this actuator will be at a frequency of 20 hertz. So based on the voltage signal, we will be able to move the mechanical part. This is the way resonators are made. Like whatever frequency we want, we give a pulse or a sine wave signal of that voltage, that frequency of the pull-in voltage going up and down, and that's how this physical object like cantilever and this plate can move. And as such, we are able to create a lot of MEMS resonators. MEMS resonators are one of the very common devices made using MEMS technology. Okay, then we saw that how this movement can be created. Like you see, suppose that we want this whole structure, this COM kind of structure to move and continuously move. And due to this movement, there will be a humming sound, say, or there may be due to this movement, we are switching on and off some circuit. Okay, such things can be done. But since it is a physical thing, a physical object, although it is in micro level, there is one problem that occurs in case of MEMS actuators, that is Stixon. They will get stuck. Okay, addition, and this can happen due to van der Waals forces. We saw that at micro levels, van der Waals forces become more relevant compared to electrostatic and gravitational forces. Although here we are playing with electrostatic force, we are creating field and all, but still the effect of van der Waals forces sometimes is too much that it will lead to just such that it will lead to Stixon in the component. Second is capillary forces, that is moisture condensation. What if that's why you see that these MEMS structures are generally very well sealed, very well packaged, because small amount of moisture can lead to a lot of changes, since it like the whole structure can be smaller than one drop of water. So you can understand that how much damage or how much change in the property it can lead to if just a fraction of a drop of water or moisture gets in. And then third is electrostatic attraction. We, since we are putting some electrostatic field, due to two different two different parts working for different purposes, but the field that is generated in one actuator might affect the other one, and that can lead again to Stickson in MEMS. So the the thing is that if we want this surface not to have this problem, what can be done? Yes, anyone? What can be done to stop this stucking and sticking of these parts over each other or on the surface? Like if you see here, this comb finger is stuck due to adhesion. It got attracted towards the substrate and it gets stuck there. And as such, the whole structure will be stuck. So, what can be done? Yes, anyone? Yeah, please speak up. It's very uh, if you think from just common sense, you can answer most of these things. These are not very complex, although like visualizing it might look complex, but in actuality, the concepts are very common one. Okay, it is just that it is being done in very small scale, very tiny scale, which we cannot see using naked eyes. But the phenomena, the structure, the concepts are very much common concepts that we use in our day-to-day life. Yes, anyone?
If it is a polished surface, sir,
Yes. So what will it do if it is a polished surface? You are in right direction. So polishing the surface, what we can achieve, what we are increasing or reducing. Suppose that we are making a wall, okay, and we don't want dirt to be attracted to it much. So we make it very smooth.
oily layer, sir.
Yeah, what? I didn't get what.
Oil layer.
Oil layer. Yes, that is the oil we can put. Yes, that will, but oil will actually attract dirt in that case. But yes, we can protect water, right? We can protect it from water using oil or some hydrophobic thing, right? So one thing is that we don't want moisture. We can put some hydrophobic substance over it, right? Not oil, but other hydrophobic substances. Like there are actually silicon itself, pure silicon itself is very hydrophobic in nature. But as soon as it comes in contact with air, it creates native oxide, silicon oxide, which is very hydrophilic in nature. Okay, so we might need to put some layer like silicon nitride, or there are other layers which can be coated over it to make it hydrophobic in it. One thing. Second is, you also said that we will make it smooth. Smoothness will reduce the chance of friction, and as such, we will have less chances of stiction. So these are some of the things. So what are the main causes? One is capillary condensation. Why it occurs? Okay, water droplets forming during drying. So when these structures are made, like beams or cantilevers, okay, some water droplet might get in it and make a like condensed form, and as such, that can lead to some capillary condensation and will lead to Stickson. Second is van der Waals forces. Since these forces become much relevant when we are at micro scale. So uh, two different parts may come so close that this force overcomes their mechanical strength. As such, it will get stick. Second is electrostatic attraction. We very commonly know that if we uh, comb our hair in winter, dry hair in winter, and then try to use the comb to attract something like some papers and all, it works. Okay, so here also it is like it will develop some electrostatic attraction, and that is why you see when we work in these MEMS and microfabrication and macro and nano fabrication, we are not supposed to be handling them directly, as well as we need to be grounded. Our whole body needs to be grounded. In the next section, where we will be talking about how these are fabricated, the first thing we will be talking about in what environment we uh, fabricate, because the environment in which it is to be fabricated has to be very clean, free from any electrostatic charge and all. You see, like, okay, yeah, I have some. You are able to see my video? Yes, everyone? Hello?
Yes, sir.
Yeah. So you see, such straps are used when working with this. Just a minute. When working with these structures, in our hand, we use such straps. These are conductive straps. Okay. So whatever charge is in our body, that will be conducted, and these are connected to the ground. Like it has wires, and it will be connected to proper earthing system, very good earthing and like grounding system, so that no charge is there when we are handling these materials, like when we are handling them even with tweezer and all, we need to be very careful that there is no extra electrostatic charge that can damage them or that can lead to some stiction. Okay, so such cares are to be taken at like fabrication level and all. Then there are other structural changes that can be done. Okay, that one is hydrophobic coating, like I think who said Venkta Lakshmi, you said this, no? That oil and all.
Yes, sir.
Okay, so so one is hydrophobic coating that reduces the surface energy, and reducing the surface energy will lead to less availability of the surface for any attraction or adhesion. Okay, so if you see the graph where we have a hydrophobic surface and a non-hydrophobic surface, so the contact angle of a hydrophobic surface and non-hydrophobic surface is different, and as such the adhesion force is much less in case of hydrophobic surface, and we so it will reduce our uh, chance of a stiction to some extent. Second is why to use water instead of water during this during the fabrication or during making of this structure. Go for supercritical drying, where drying is done using mostly carbon dioxide in supercritical form. Supercritical state, anyone knows what is supercritical state of carbon dioxide? Yes, anyone? Please speak up, don't be shy. It's fine. You are not being judged. Please speak. Anyone? Yeah, Kunta Harika, are you there? Yeah, please speak up. Like, I will not be able to see messages frequently. Okay, so please speak. You can unmute and speak up. Yes, anyone?
No, sir.
No? Okay. So supercritical, I think, okay, that image is not here. If you just do a small Google search over, do a small Google search, you will find that there is one unique property of carbon dioxide, that is supercritical state, where it remains in all the three states, solid, solid, liquid, as well as gaseous state. Okay, there is a point. So, or super cooled liquid, it is said. So, what it is done, what its use is that it can be used to clean these surfaces. Water is mostly used to clean the surfaces during the fabrication of this, and that also, that water is not the common tap water we are talking about. That is deionized water, very pure, no ions, nothing at all. But still, that causes problem to our structures. To overcome this problem, supercritical drying is used. That means CO2 in its supercritical state will be used, and as such, since it is uh, acting both as liquid and gas, so it will take out the like whatever particle is there, it will like dissolve it and take it out, and it will evaporate. It will not remain there. As such, we can avoid any interaction with water to prevent capillary forces. But again, there can be cost constraint, as well as using supercritical drying is not that convenient. If we talk in terms of like fabrication, it will increase the cost, as well as it is a difficult as a and cumbersome process. Third is increasing the like surface roughening. That means reducing the contact angle, make the surface very smooth, and as such reduce the contact angle. Then third is a practical approach when you see that something is stuck. So instead of using the voltage to pull it, suppose that it is stuck there, you push it. Like put a negative voltage or anti-stiction, electrostatic anti-stiction, that is a repelling voltage that will move it in the opposite direction, and it will come out. So it can even be made that after, say, working for, if this device works for 24, 25 hours, after this, there will be a repelling voltage applied for, say, 2 minutes. And if something is stuck, it will force it to unstuck, and then again it will start working. Such, such mechanisms can be used to prevent stiction. Okay, so what we have seen is that this is a image of one actual device. So you see upper electrode, and this is lower electrode, and in between there is air. Okay, and this movement is controlled using the voltage sources here. These are the pads where we are putting the voltage sources, and as such they are like, that is controlled here also. This is the top moving electrode, this is fixed electrode. Okay, and this is moving electrode. So what we have seen is that electrostatics is used in MEMS actuation. It is one of the key mechanism for key force for MEMS actuation. It increases with voltage and can lead to pull-in instability. Yes, yes, Kunta, you are saying something. Okay, so coupled electromechanics determine system dynamics. That is, we saw that it is not only due to electrostatics that this thing occurs, this actuation occurs. It is due to the balance of the mechanical force and the electrostatic force that leads to the whole MEMS actuation. Stiction is a significant failure mode in MEMS caused by capillary and adhesion forces. To prevent stiction, we involve coating special drying like supercritical drying and anti-stiction mechanic like smoothing the surface and all these things. So any questions till here, anything you are not able to understand or you want to add, please feel free to do that.
Sir, how the spring is constructed, sir? Is it with uh, thin layer material or
It is not a spring in actual sense. It is like you see this structure is hanging in air. Okay. So why is it hanging in air? What can be the reason for its hanging in air? Or if we see about most of the houses that are made RCC houses, okay, we have small, like our house on the ground floor is like this. Okay, this is the door and all, and we see a small balcony kind of structure made hanging in the air, right?
yes,
And
sir?
then, yeah, so how this structure remains stagnant, how it remains in air?
That we are calling cantilever beam structure, sir.
Yeah, so this cantilever beam structure is held in its position due to some mechanical strength, right? And that mechanical strength can be like for our studying purpose, we can like we can ec- make its equivalent structure as if it is being held by a spring above. Okay, so
Okay, sir.
there is no spring. It is
Okay, sir.
the mechanical property that uh, we are representing by spring constant and all. There is no spring, right? So such structure, when we are talking about cantilever or such structure, so what mechanical force is holding this structure, like the top electrode, in its place, that we are representing by the spring. And if you talk about can we make a spring or not in MEMS structure, that metallic inductors or springs are one of the most difficult part that microfabrication and nanofabrication is unable to make. That is uh, that is why you might be seeing that still transformers still come in forms of big wire bond structure and all, because transformer inductors, this inductor is a component that I have not seen yet, and I have not even heard that a inductor kind of component has ever been made. Like there has been attempt, but it is still not a successful thing in case of uh, semiconductor fabrication. That's why you see capacitors inbuilt into the circuit in chip level, but inductors are not inbuilt yet. Yeah, any other questions, anyone? Yes, anyone like to ask something, add something? Please feel free. Okay, so should we go with questions and answers? Okay, this you people have to answer. What is the fundamental law governing electrostatic force between two charges? Newton's second law, Gauss law, Coulomb's law, or Ohm's law? Yes, anyone? Yes, anyone? We started today's lecture with this. Yes, please speak up. Yeah, Kunta Harika. Yeah, please unmute and speak up. I will not be checking the messages. Okay? Yes, what you are saying, and let everyone discuss. Let's not have a message-based conversation, please. Yes, anyone? So, when we talk about electrostatic force, that is defined by the Coulomb's law. Okay, and that gives the force as 1 upon 4 pi epsilon naught q1 q2 upon r square, where q1 and q2 are charges and r is the distance between them. Okay, when we are talking about this q1 and q2 we are assuming as point charges. That means they don't occupy space, they have a very limited space and they are confined in there. So next is, what is the unit of electric field intensity? Newton per coulomb, farad per meter, ampere per volt, or coulomb per second? Yes, anyone? Please speak up.
Amperes
Yes,
per volts.
ampere per volts. Okay. Yeah, any other answers? Electric field intensity. Okay. So it is,
We said, oh, sorry, sir, not
yeah. Okay. Not an issue. Even if you are wrong, not an issue. We will be discussing this anyway, right? So electric field is defined as force per unit charge. Okay. So force, we know force is given in terms of Newton, and Q, that is charge, is given in terms of Coulomb. Unit of charge is Coulomb. So the electric field intensity E, or electric field, is given by uh, has the unit Newton per Coulomb. Okay. Okay, now let's come to what we have been discussing throughout the lecture today. The capacitance of a parallel plate capacitor in free space is given by free space. When we are saying, that means the thing that is in between, this is air. Okay, is given by C equals to epsilon naught A upon D, C equals to A upon epsilon naught D, C is equal to Q upon V, C equals to epsilon naught D upon A. Yes, anyone? Mm, someone said she's in first year, right? Yeah, Bidisha, you are in first year, right? Electronics first year, right? So you must you must be answering this. Yeah, please answer. This is something you have read freshly. Yes. What we discussed when we talked about capacitance, increasing the surface area will increase the capacitance or decrease the capacitance. Anyone? Yes. Akhil, are you there?
Option D.
Option D. Okay. Okay. Yeah.
No, sir, option B.
B. Okay. Fine. And any other answers? Okay. Tell me one thing, anyone, that the dielectric constant, that is the dielectric constant of the medium, increasing it will increase the capacitance or decreasing it will increase the capacitance. Yes. Anyone?
yes, sir.
Yeah.
Epsilon A by T.
So A. Okay. So why not B? Why A? Someone said B, someone said A. Now you have to defend which one is correct and why. Yes, and
In the free space, the relative permittivity epsilon r is 1, sir.
one. So in that case, even if it is one, but the formula why epsilon naught is in the numerator and not in denominator. Yes, anyone? Yeah, Vidisha, why it is in denominator, not in numerator? Yeah, any
Capacitance is proportional to permittivity, sir.
permittivity, yes. So actually it is just a constant, but the constant is taken as linear. It has linear dependence. Okay, it is not inversely proportional. Yes, you were adding something, Vidisha. Yes. Hello. Anyway, that is the first. That is, it will depend on plate area and plate separation. But the dependence on plate separation is inverse, and the constant is epsilon naught. Okay, it can have other constants also, but epsilon naught is taken as linear dependence. So more the permittivity, higher will be the capacitance. Okay, let's move to the next question. The potential at a distance r from a charge q in free space is there. There is a charge q. Okay, and here we are standing at a distance r. Okay, so what is the potential here due to this charge? Potential simply means its effect or its strength to pull up a charge. So anyone?
Option A.
A.
Maybe.
Okay.
Yes.
Mm, anyone else? It comes from Coulomb's law only. Okay. It is given by q upon 4 pi epsilon naught r. So v equals to E upon R, that is field by distance, and E in turn is the force due to a point charge acting at a unit test charge. So F we are defining as 1 upon 4 pi epsilon naught Q1 Q2, right, upon R square. So we are saying that Q1 is there, but Q2 is equal to 1, and that means E equals to 1 upon 4 pi epsilon naught Q1 or Q by R square. Again, dividing this whole by R gives us, no, sorry, E at R, at distance R, no, not E, at distance R. So multiplying it with R will give us the voltage V equals to this R will cancel out. So we'll get Q upon 4 pi epsilon naught R. Okay, this is very important in terms of uh, electronics or electrical concepts, because this is the uh, potential, that is like what effect it will have. This forms the gradient due to which this charge flows and all. So these are fundamental equations you should know. And this is correct. Very good. Okay. So next is Gauss law states that the electric flux through a closed surface is proportional to total charge enclosed, charge squared, distance squared, or applied voltage. These questions I am asking from Sir's lecture. Sir have covered these things. If you have seen the first, in first lecture, sir talked about this. Yeah, anyone? Yeah, please. Electric flux. Anyone?
Total charge enclosed by that surface.
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 Uh, yes, very good. So, uh, how do we define flux? What is the symbol for flux? Yeah, yeah. Speak up. Not sure. What is? How do we represent flux? Yeah. Anyone else remembers how do we represent flux? Phi E. And by Gauss law, it is given as total enclosed charge upon epsilon naught. Okay, so it will depend on total charge enclosed. Okay, so upon epsilon naught. Okay, that is the uh, loop integration of the total field. Okay, so we'll not go that in equations and all, but we should know these equations. Like these are some standard equations to start with in this field. We have to know. Okay. The electrostatic force between two charged plates of a MEMS device is proportional to V square 1 upon V, Q, or D square. We have discussed this, so I expect anyone will answer, please. Yes, Kunta, Harika, or Akhil, you can also answer. Yes, anyone there? Yeah, Akhil, are you there? Hello, Akhil ji, are you there? Yes, anyone?
No, sir.
No idea? Okay, so we saw this uh, previously that epsilon A V square upon 2D square. So it is having a quadratic dependence on voltage. So if we increase the voltage by say 1 fold, we will see that the increase is squared. The increase in the electrostatic force is squared, and as such, the F electric will increase very fast. That means at 1 voltage, whatever the force was there at 2 voltage, that force will be quadrupled. It will not be the same. So it is not that at 1 voltage the distance, the plate is moving say 1 micrometer. At 2 voltage, 2 volt, it will move 2 micrometer. No, it will move around 4 micrometer. So this force increases quadratically based on the voltage. That is why we can control it very well using the voltage. Next is the force required to separate two charged plates in MEMS is called magnetic force, mechanical restoring force, dielectric force, or electrostatic adhesion. Yeah, anyone? From the name itself, you can guess. Suppose that due to the voltage we applied, two two plates stuck to each other. So what force will be able to bring it back to its position? Will it be a magnetic force? Will it be a mechanical restoring force, or dielectric force, or electrostatic adhesion force? Yes, anyone? Okay, let's solve this problem together. So, what are the two options that we can remove at first? Anyone?
And and
A and? Yes. A and what was the second option you were saying? Hello.
sir, there is a confusion. According to your arrangement, you have shown two capacitors and
Plate.
a spring action. That
Hmm.
means whether it is mechanical restoring force according to the spring action. But according to charged particles, it looks like a D, but there is a adhesion word is there.
It is saying that separating two charged plates. So plates are already charged and they have come together. Now, what force will be able to take it back? It is being pulled by the mechanical force only. It will try to restore it. So even if we go by like removing two options at first, so we can say that magnetic force, we have seen in the previous lecture also, magnetic force is not there in case of MEMS devices. Then there is nothing called as dielectric force. So we can remove these two. Okay. Now there are two things. Mechanical restoring force, electrostatic adhesion. Adhesion will try to bring it closer, not separate it. We have to separate it. So this is also one. So only even if we go by eliminating some options, we will get mechanical restoring force. Okay. This is the force opposing the electrostatic attraction that prevents the collapse. That is why these plates don't stick together since there is some mechanical strength. But if we go beyond certain limit, such a force such that it will break or something, in that case, this mechanical restoring force will not be there. Like if this plate breaks, what we are representing by spring, that means it is still connected to the support, mechanically connected. If that breaks after that, it will be free and it will not come out. Okay. The electrostatic pull in voltage Vp for a MEMS parallel plate actuator is given by which of these equations? Yeah. Anyone? We have seen this equation, right? Yes. Anyone?
B side?
Okay. Yeah. Any other answers? The pulling voltage will not only depend on electrostatic force, but it will have some component from mechanical
Mechanical
forces.
forces.
Yes.
Yes,
Yes, Vidisha,
yes,
you are saying
Vidisha, you
something.
are.
Hello.
Sir, option A.
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 And why?
And
Uh, cause
See,
B.
like if you
Like if
check the
you check the
derivation,
derivation,
it is
it
what
is
comes.
what comes.
But
But
there are
there are
some things to
some
keep
things
in
to
mind
keep in mind
that
that
this
this
uh,
uh,
pull-in voltage will
pulling
depend
voltage
on
no,
spring constant
string
because
constant because
yeah, there is some
there is some
echo coming
echo
from your
coming
side.
from your
Can you
side.
mute?
Can you mute?
Yeah. So this voltage will depend on the mechanical restoring force also. So how much is the mechanical strength or mechanical restoring force will also determine the pulling voltage because they have to be equal. We saw that F mechanical must be equal to F electrical for uh, have for having this equilibrium, and this equilibrium is achieved using by applying the pull-in voltage. Okay, so this will depend on factor K as well as D naught. Okay, but the complete derivation, if you check in Sir's lecture, he has discussed how this is derived. Although I think when we are talking about MEMS sensors, we should know these equations, but derivations are important when we are discussing about the fundamentals of this in basic physics and all. But from the fabrication point of view and all, you should know the equations because based on this, different calculations might be needed when we are making sensors or actuators. Okay. Electrostatic MEMS actuators operate by magnetic interaction, voltage controlled attraction, mechanical contact, or piezoelectric deformation. Yes, anyone? This I think we have discussed multiple times. So how these actuators are working? Anyone like have you people understood what this actuator is doing actually? What is it actuating? Or if you have not understood, please speak. I will try to explain it. Yes, anyone? What it does in terms of like MEMS? Yes, anyone? Okay. I think you people have not understood it. So let's make it simpler. Suppose that with suppose that we are making such a mechanism that will count like after some time or say some voltage, a work has to be done in presence. So what we have to do is that suppose that we want that this the structure is to be hit by uh, another structure, say after every after every 20 seconds. Okay, so that some current will flow through it after every 20 seconds and some other work has to be done. Okay, so let's take in a macro system. Okay, so what we are doing is that we have put a plate over it. This is a cantilever kind of structure which is movable. It can be brought towards here, and this is a fixed plate. So fixed plate, and this is moving plate, and all the connections are done through here, and this whole structure is fixed like this. This is a fixed structure. We have a voltage V here, some connections are done and all. So what we are doing is that to keep it apart, we are putting some voltage, say 5 volt for 19 seconds, and then we are making this voltage 0 volt, and then so when it is 5 volt, this will come here and it will get disconnected. When it is 0 volt, it will come back to its original position and it will make a connection. After 1 second, so we are again increasing the voltage V to 5 volt, and this cantilever will come towards, it will get attracted, it will move a bit in. I am making it like bending, but it will not bend since it is it can be either on a membrane, so it will try to just pull in. We can say let's make it on a membrane, so the whole membrane will try to move in, and as such this connection will get disconnected. So we are doing this whole thing in, say, these distances are in micro level. We are doing all this circuitry in micron level. Okay, that is the work of this cap MEMS actuator, that we are moving some parts, physical parts, using electrostatic control, that is by providing voltage pulses and all. So now can anyone tell what is the electrostatic MEMS, like how the MEMS actuator operate? Yes, anyone?
Voltage controlled attraction.
Yes, very good. Now clear that we are moving objects, or like we are moving some parts using voltage, and the voltage is not just that giving a voltage something will move. We will have changes in the voltage to have some movement. That is, we might be giving some pulse, like up, on, off. We can giving be sine waves, like suppose that we want that this connection should be very regular. It should happen 20 times, like it should be connecting, disconnecting, connecting, disconnecting 20 times in a uh, second. So we will put, instead of this voltage, we will put a signal of, say, 20 hertz, that is changing 20 times from 5 volt to 0 volt in 1 second. Okay, so as such we can control this structure. Fine. Increasing the plate area in a MEMS capacitor will decrease electrostatic force, increase capacitance, decrease pull-in voltage, or both B and C. Yes, anyone? Remember the equation of capacitance. C equals to epsilon naught A upon D. So if we are increasing A, capacitance will increase or decrease? Yes,
Capacitance increase.
increase. So option B is correct for sure. Now, if you see the equation of pull-in voltage, so we saw just before, is there any relation with A here? A is in the denominator. So since A is denominator, pull-in voltage will increase or decrease?
Decrease.
Decrease. So C is also correct. So we can say both B and C are correct, right?
Yes.
What equation describes the motion of a MEMS actuator? Anyone? We saw that electric force and mechanical force should be equal to understand the motion of a MEMS actuator. Okay, and mechanical force is given by M x double derivative plus C x single derivative plus kx. Okay, so we are saying that this is equal to F electric. So what will be the correct answer? Since we are considering it as a mass spring system, that is, it is having some whatever force is there that we are represented using. Like in if we talk in terms of electronics, whatever may be the system, it might be looking as a single component, like a transistor. If you see, it is a single component, but we represent it in terms of resistance, capacitance, and inductances. Right? Everything can be modeled using resistance and capacitance. So if we talk in terms of mechanical, since these are electromechanical devices, right? So micro electromechanical systems. So from the mechanical concept, everything can be uh, described as a combination of springs and masses. Okay, so they are representing in terms of spring and masses. That is a equivalent way of representing it. So so that we can take out some parameters. So the parameters here will be the mass, the spring constant, and these things. Okay. So what will be the correct answer, equation that describes the motion of MEMS actuator? Yes, anyone? So it is A. Okay. In MEMS, electromechanical coupling refers to interaction between electrostatic and mechanical forces, heat transfer in MEMS, capacitance variations, or magnetic force interactions. Yes, anyone? I'm audible, right? You can hear me.
Yes.
Audible, sir.
Yeah. So what will be the answer for this? See, the term itself means electromechanical, electrical and mechanical coupling. So it is interaction between electrostatic and mechanical forces. That means electromechanical coupling. The pull-up effect in MEMS occurs when electrostatic force equals the mechanical restoring force. The damping force exceeds the elastic force. The actuator moves linearly. The capacitance decreases. Pull-up effect VP or V pull we have seen. No? When will it occur? as we have seen that this is the voltage when it will be able to overcome the mechanical restoring force, and that is the point when the pull-in effect will occur. That means the plate will try to pull, like fully touch the other plate. The moving plate will try to move towards the fixed plate. That is when the pull-in effect occurs. That will make it like it will try to touch the plate. Okay, overcoming the mechanical restoring force. MEMS devices exhibit bistability when two stable positions exist, the system has no equilibrium, there is infinite displacement, the system is unstable. Bistability means there will be 2 points, like at one point it will stop and then another, like in equilibrium, there can be two equilibrium positions. Okay, one, it will stop at a fixed point, and then if we increase in further, it will again go to the next position. So what will be the correct answer then? Yes, anyone?
Two stable positions.
Two stable positions, that is A. Okay. Feedback in feedback control in MEMS actuator is used to. So although we are this part sir has covered, so I didn't cover much, but we have to understand that there, whenever we are making such systems, feedback is an important part. That means what we thought will happen is actually happening or not. And if it is not happening, like suppose that we wanted the movement of 20 microns to occur, it occurred or not. If it occurred, fine, no correction needed. But if it is not 20 micrometer, what is the difference? That means whether it is 18 or whether it is 22, 23, that part has to be corrected, and that is a feedback control. That means that that will change the voltage that we were giving. I said no, that on the fixed plate V we are giving, and moving plate it is 0 volt. Okay, so suppose that we wanted that giving V equals to 5 volt, made it make it move till here, but when we gave 5 volt, actually it moved till here only. So by the feedback mechanism, that is feedback control circuit, it will give the control signal to increase it since it has not reached the exact position. So it will increase say to 5.5 volt, and now again instead of going to the linear position, next time it reaches till here. Again this feedback mechanism will trigger that it is too much, and it will decrease it, try to decrease it, and then say it gave 5.3 volt, and then it can correct. Now the feedback mechanism will give zero output, that is, it is correct. So instead of 5 volt, it will give 5.3 volt. Over a period of time, this might change, and then it might change to 5.35 volt. Then after say working for some more time, it becomes 5.45, 5.5, like that. Okay, so these corrections are done using feedback control. Okay, so what might be the purpose of using this feedback mechanism? To increase instability, to reduce the pull-in effect, enhance damping, or reduce power consumption? Yes, anyone?
Looks the reduced power consumption because we are changing the voltage from 5, 5.5 like 5.3 etc.
But the purpose is the purpose to reduce power
But here instability is there, sir. It should be increased stability, na, sir.
is used to increase stability. Yeah, and other thing, It should not be increase in stability. It should be increase stability as well as reducing the pull-in effect. It is used to increase stability and reduce the pull-in effect. That means it might be happening that the pull-in effect is too much. That I saw now that here. What we want position here. We want this X position, but the pull-in is too much. Okay. So pull-in is higher or it can be lower. So both answers will be correct. Reduce the pull-in effect or uh, increase the pull-in effect. But this option is not there. Okay. So we should go with option B. And a combination of these two will increase stability, not instability. So you like you didn't fall in trap of instability word. So the correct is answer is to reduce the pull-in effect as well as to increase the pull-in effect. Both will be there and increasing the stability. Now next is what is Stickson in MEMS? We talked about Stickson. Okay, so it is electrical breakdown, unwanted adhesion of surfaces, resonant frequency shift, or voltage instability. Yes, anyone? What is Stickson? We talked about this, no? Yes, anyone?
B, sir. Unwanted adhesion of surfaces.
Of surfaces. Very good. So, what is the primary cause of Stickson in maps? Electrostatic force, van der Waals forces, gravity, or magnetic force? We talked about this that in microscale, van der Waals forces are much stronger than electrostatic forces. Although we are here playing with electrostatics, but the van der Waals forces will still try to disturb us since they are more prevalent. They are more dominant here and they lead to Stickson in MEMS. Gravity is uh, gravity is irrelevant in MEMS because the mass of the bodies are too small. Magnetic forces are not there until unless purposefully introduced. Now, some materials with magnetic properties are being explored. Electricity and ferromagnetism are being explored a lot, but they are still not like present that much in MEMS devices. Which method helps reduce Stickson? Supercritical drying, hydrophobic coating, using methanol instead of water, all of the above. Yes, anyone? Yes, anyone? So we talked about super like since water is the problem, we remove water. So supercritical drying we can go for. Hydrophobic coating will help like surface not getting not getting that much of like addition of water. Third is methanol instead of water. Methanol is again a good solvent and pure. We are talking about pure methanol, not about this mixed with water or diluted with pure methanol. If we are using, in that case also it will replace water. Like it will evaporate. It will not remain there. It will evaporate, and that can help reduce Stickson. So all of these are correct answers. Which process is commonly used in MEMS fabrication to prevent Stickson? sublimation drying, laser annealing, ion implanting, or plasma etching? Yes, anyone? When we are making MEMS, okay, what is the thing that we are doing? So, sublimation drying is one process that prevents stiction. Again, it is way of drying where we are not, we are ensuring that there is no water, since everything is uh, like it is the same as supercritical one, where liquid directly uh, like evaporates instead of uh, in liquid phase drying we are using such liquid which will directly evaporate. Stiction failure in MEMS mainly occurs in bulk micromachining, surface micromachining, 3D printing, or photolithography. Anyone knows these terms? Bulk micromachining, surface micromachining. See, when we are making MEMS structure, uh, traditionally when we were talking about this semiconductor fabrication, most of the things were, when we are talking about silicon wafer, right? I said that it is very thick, thin, around 350 micron. To nowadays, even if we are going for 8-inch, it will still be uh, not like less than 1 mm thickness. Okay, but the whole processes that occurs in actually most of the processes that occurs in the top maximum 500 nanometer. Okay, when we talk in terms of semiconductor fabrication, most of the things that are occurring in top 500 nanometer only. 350 micrometer, you can understand, and this is just half micrometer, 0.5 micrometer, or maximum to maximum, like old days it was happening in 5 to 10 micrometer. So most of the things that are occurring on the top surface only. This is called as surface micromachining, where structures are made on the surface only. When I talked about making a membrane today, like everything from below is etched out. Okay, such things where we are removing a bulk of our uh, device, a bulk of our substrate, or on the top we are making some trench. These things are called as bulk micromachining. Okay, and 3D printing we know is not related to microfabrication, but where we are making a 3D structure by depositing a layer by layer, one above another, and they are getting added, like added due to heat, and we are making some structure. Okay, I have 3D printed structure here, and photolithography is a process of making patterns. So, what in what part stiction failure can occur? Bulk micromachining or surface micromachining, 3D printing or photolithography? Yes, any answers? This is the last question, at least answer this. Yes, anyone? The sticking of things will occur in smaller objects or larger objects? Anyone?
Option B.
Option B, that is surface micromachining. Reason being, here the structures are much smaller in size, and that's why they have more chances of stiction failure. And in bulk micromachining, since the structures are much bigger compared to have a good aspect ratio, they will not suffer much from stiction failure. 3D printing is a separate thing, and photolithography is where we are making patterns on a surface. So in this, we will not be using photolithography very less, like such MEMS devices are not, although they use a lot of photolithography, but the structures that are made, they are not machined, like not carved out. It is just a technique to define the pattern. We will be talking more about photolithography in the next section. In the next class, we will be like next week, we will be starting from how this, like we saw the fundamental theory and all, which you most already be knowing. Okay, now we will be going into how these things are made, how these structures are actually made, how these sensors are actually made. So we will start with what is silicon, why silicon, how to etch out silicon, how to make such cuts and all in silicon, how something is deposited over it, how something is removed over it, what are the tools and techniques, and some lithography technique, like how this patterning is done. So any questions till here? Any doubts, any questions, anything you are not able to understand? Please ask. Anyone?
Sir, in these three interaction sections where I felt that only capacitive property is dominating now, sir. Is it true, sir? Sir, voice is not coming, sir. Yes, sir. Okay, sir. Sir, I am faculty of instrumentation, sir, in Andhra, sir. So I want to know the MEMS, sir. Thank you, sir.